Okay, so we're going to continue with the video. I don't have anybody in here right now. It's 4th hour and they're all at the assembly, so I thought this would be a good time to catch up on some of these to make sure we get them all done. So the one we were ready for here is number 7. Decide which of these half cells would be the anode. Well, we just decided which one was the cathode, so at this point it should be fairly simple to decide which one is the anode. So the anode half reaction is going to be taking place at the copper. Alright, so the half reaction there, again, we've got copper 2 plus and silver plus in these. Okay, so that half reaction would be copper, solid copper, going to copper 2 plus 2 electrons. Okay, so there's your balanced anode half reaction. And again, you could think about this in terms of, we did this last year. We put copper wire into a solution of silver that had Ag plus in it, and when that happened, the copper started to dissolve, started to form copper 2 plus in the solution, so it started to turn blue, and you saw some of the solid silver plating out on the copper, forming silver crystals. Okay, so you can kind of figure it out that way too, just remembering what you have seen in the past. Okay, next question. The overall cell reaction. So again, the cathode reaction that we talked about is the Ag plus an electron going to Ag solid. The anode reaction, which is the oxidation, is going to be copper solid going to copper 2 plus 2 electrons. Okay, so then that's going to show you here that in order to write the overall reaction, we've got to get the number of electrons balanced, so we have to multiply the top equation by 2. So then what we're going to end up with here, I don't know if I have room to write this right here, 2Ag plus, and I'm going to leave out the electrons because they're going to cancel out anyway, plus copper solid yields 2Ag solid plus Cu2 plus. Okay? And the reason we have to have 2's in front of the silver and the solid silver is because we have to balance the charges as well. Okay, so if we didn't have that, the atoms would be balanced, but there would be a 1 plus charge on this side and a 2 plus charge on this side. So putting a 2 in front of the silver, 1 plus, and in front of the solid silver takes care of that. Okay, so there's your overall cell reaction. The direction of the electron flow. Okay, so again, we have labeled this as the anode. We have labeled this as the cathode. Okay. What that means is, at the cathode, that's where reduction is occurring. That's where the gain of electrons takes place. At the anode, that's where we're losing electrons. So the electrons are going to flow from the anode to the cathode. Okay? And then we also want to show the direction of the ion flow in the salt bridge. So now that we're thinking about the direction the electrons are going to flow, if we didn't have a salt bridge in there, as the electrons are leaving the anode, this would have a tendency to become a little bit more positive. Okay, so in order to counteract that, the NO3 minus is the anion. The anion NKNO3 must be traveling into this cell to neutralize it. Okay, and again, you know, we could just pick the other one over here. It's going to be the K plus because that's the other part of the salt bridge. But as the electrons flow into the cathode, this would have a tendency to get more negative over time. But the K plus can flow into that solution and neutralize it. Okay, so that's the direction of the ion flow. The standard cell potential for this cell, we want to verify the voltmeter reading is correct. Okay, so here's the voltmeter reading. So in order to calculate the standard, we take the cell potential or reduction potential of the cathode minus the reduction potential of the anode. Okay, so when we do that, the reduction potential of the cathode, which we have decided is the silver, is going to be 0.80. And we subtract the reduction potential of the anode, which is the copper 2 plus, copper going to copper 2 plus, so that's going to be 0.34. Okay, so when we subtract those two from one another, we should end up getting, let's see if I can do this in my head, 0.46. go 0.46 volts. Obviously it's right on the voltmeter. I could have just looked at that. So 0.46 volts is going to be the correct reading. So the voltmeter is correct. All right, next question. Write the net ionic equation for the reaction of iron metal with hydrochloric acid. Okay, so the net ionic equation here, you have to make sure that you're writing net ionic on this test and on the AP exam. You just got to get used to that. Okay, now if it helps you, you can write the overall equation first. Okay, but just looking at this, well, yeah, I'll just write the overall equation because I'm not sure exactly where you guys are as far as understanding this. Okay, but Fe solid plus HCl, it's going to yield, and HCl will assume that's aqueous because it's dissolved in water typically. So then that would make Fe, take your pick, I guess, FeCl2, we'll say it's iron 2 plus. And again, that would be aqueous plus H2 gas. Okay, so this is single replacement as it's written that way. Now the net ionic equation for this, the chloride doesn't do anything. So what we end up with here is solid iron plus H plus yields Fe2 plus, based on the way we have written it, plus H2 gas. Okay, and because we have two hydrogens, I should have balanced it up here. But we can also balance it down here. Okay, and that balances the charge as well, so everything is good. That's a good net ionic equation for that one. Okay. Now we want to write the, now again, the nice thing about the AP exam is they don't give you reactions that don't work. So you don't need to check your activity series, or, sorry, your reduction potential chart. You don't need to check that to make sure that this happens. If you do check it, just for fun, you can see that the iron here is below the hydrogen. Okay, so it would have a tendency to get oxidized when you place it in H+, and the H+ would have a tendency to get reduced because that's higher up on the reduction potential chart. So this actually does occur, okay? That actually kind of answered the bottom of this question here, right? The oxidation and reduction half reactions. So solid iron yields Fe2+, and we got to write in the electrons when we were writing the half reactions to balance out the charges. That's going to be my oxidation half reaction. Okay, and then my reduction half reaction would be the 2H+ yielding, sorry, plus 2 electrons yields H2 gas. Okay, and again, you can tell based on where the electrons are placed, because this one's gaining electrons because electrons are on the reactant side. This is going to be a reduction. Okay, so hopefully that makes sense to you. Again, it's maybe better for you to start up here and then make the net ionic from there. Some of you are getting to the point, hopefully, where you can just start here because you can kind of see what's going to happen immediately. Typically, when you add a metal to hydrochloric acid or any acid, if that metal is below hydrogen on the reduction potential chart, then it's going to tend to get oxidized and it will make hydrogen gas. Okay. Predict whether or not the following reactions will occur. We kind of did one like this at the beginning, so we'll just hopefully go through this quickly. On this one, what you have to really identify here is the oxidation and the reduction that are occurring. Okay, so Ag plus going to Ag, that is a reduction. Okay, F2 going to F minus. I'm sorry. No, that's right. That's a reduction. F2 going to 2F minus. Also a reduction. Well, I don't think that happens. So if you have two things getting reduced, nothing's getting oxidized, obviously this reaction does not occur. Okay, so no. It's not that that reaction is not spontaneous in the forward direction, it's just that that reaction would never, ever occur. Okay. Alright, so Pb2 plus aluminum yields Pb plus aluminum 3 plus. Alright, so we've got Pb2 plus going to lead. That's a reduction. And we've got aluminum going to aluminum 3 plus. That's an oxidation. So let's check our chart here and see if that's the case. In order for this reaction to occur, that would mean that the lead, the Pb2 plus Pb, would have to be above the aluminum on the reduction potential chart. Okay, and it is well above aluminum on the reduction potential chart. So this one actually, this one will occur, so we can put yes, or we can put spontaneous in forward direction. Or, I guess for that matter, we could also put positive voltage. Or, if we're talking in terms of Le Chatelier or equilibrium, we could say product favored. Okay? You can use any of those terms really to explain, yes, this reaction is going to occur in the forward direction. Okay. Lithium plus Ba2 plus. Alright, so we've got lithium being oxidized here. We've got the Ba2 plus being reduced. Okay, so if you look at your chart here, lithium would have to be below barium. Barium would have to be above lithium on the reduction potential chart. And it is, just barely, but it is. Okay, these are two species that neither one of them really want to get reduced. But when you put the barium with the lithium, it will get reduced because the lithium wants to get oxidized more. So this one, yes, would also occur. Okay, and then see the above here for all of the other ways that you could say that. Okay, standard cell potential for the following reaction. Again, it's getting a little repetitive, so hopefully you guys are getting it. But to find the standard cell potential here, you just find the reduction potential of the cathode minus the reduction potential of the anode. I will say this, in case you're watching this video, this middle half is probably more of the stuff that you are familiar with. That's one of the reasons that I'm going over it when there's no one here. The tough stuff is towards the end of this thing, so where you start relating it to equilibrium and delta G and all that stuff. Okay, so you definitely want to take a look at that. Okay, so what we have to figure out here is what's the cathode and what's the anode. Sn2 plus is going to Sn4 plus here. Okay, so as that happens, Sn2 plus going to Sn4 plus, that's an oxidation, which equals the anode, and ox, right? The Fe3 plus is going to Fe2 plus, so that's a reduction. That's going to equal the cathode. So now that we know our cathode and anode half reactions, we can just look those up on our chart. The reduction potential for the cathode here, iron 3 plus going to iron 2 plus. Let's see. 0.77 volts. Okay, minus the reduction potential of the anode, which is the Sn, that would be Sn4 plus going to Sn2 plus. It's 0.15 volts. Okay, subtract those two from one another, and you will get your voltage. I think I can do this one in my head. 0.62 volts should be my voltage for that particular reaction. Okay, that's the standard cell potential. Alright, now we're getting into the electrochemistry stuff. What current in amps is required to plate out 1.22 grams of nickel from a solution of nickel 2 plus in 1.0 hours? Okay, so they're asking us for the current here, which means eventually we're going to be using I equals Q over T. Okay, we're going to be solving for this. In order to solve for that, we need to know our current, sorry, not our current, our charge in coulombs, and we need to know our time in seconds. Okay, they already gave us the time, we just have to convert this to seconds, but we got to figure out our charge, and the only way to do that is to do some stoichiometry starting with the 1.22 grams of nickel. Okay, now the half reaction that's occurring here, we're starting with nickel 2 plus, so in order to plate out, in order to make solid nickel, we must be adding 2 electrons here. and that's going to make solid nickel, okay, which is what we're doing in this particular process. Okay, so if we start with 1.22 grams of nickel, probably the next best thing to do is to go 2 moles of nickel. And again, we need to write balanced chemical equations. Anytime we're doing stoichiometry, that needs to be the first step. So I just kind of did that. I assumed it. Grams of nickel, 58 we'll round to 58.7. Okay. Then we can go from moles of nickel, 2 moles of electrons. For every 1 mole of nickel that gets produced, there are 2 moles of electrons required. Okay. Then we can go from moles of electrons to charge using Faraday's constant. Okay, there are 96,500 coulombs in 1 mole of electrons. Let's just use that conversion factor, and that should get you where you need to go. That'll help you solve for the charge. Okay, so that's going to give us 4,011. I'm not going to round until the end here. 4,011 coulombs. So then if we're finding the current, the I, that's going to equal 4,011 coulombs divided by our seconds. Okay, now I actually need to do that real quick. I'm sure that you can do this in your head, but I'll just in case you can't. 60 minutes in an hour. 60 seconds in a minute. Okay, so this is going to be 3,600 seconds. It's 1.0 hours. So that's just 2 sig figs there. Okay, so then we divide that by the 3,600. That's going to give us a current of 1.1 amps. And we look at our sig figs. Okay. So there's that one. Hopefully that makes sense. I think the electrolysis stuff is fairly easy. The process is usually basically the same. You're just going to use the I equals Q over T and then do some stoichiometry here to figure out the rest of it. Okay, how many grams of CuS are obtained by passing a charge of 10,800 coulombs of electrical charge through a solution of CuSO4? Alright, well this one doesn't really include amps, so we don't need a time. They're just telling us this is how much charge we're passing through. So we've got 10,800 coulombs of electrical charge, and we should be able to go straight from coulombs to moles of electrons. Okay, so in 1 mole of electrons, again, there's 96,500 coulombs, so this helps us to know how many moles of electrons we have. Then we can go from moles of electrons to moles of, what we need to do is moles of CuS. If you get this far and you get stuck, then hopefully that reminds you that the first thing you always need to do with these stoichiometry problems is a balanced chemical equation. Okay. Whoops, that's wrong. Not CuS, sorry. It's supposed to be just Cu. How many grams of Cu? Okay, so we've got CuSO4, and it's a solution. So it goes, well, maybe it doesn't go without saying, but when we put this in solution, it's Cu2 plus and SO4 2 minus. Okay? So then when we do that, when we pass the charge through that thing, then some of that copper 2 plus is going to plate out and make solid copper. So our reaction here is Cu2 plus 2 electrons yields solid copper. Okay, so that tells us our ratio here. For every 1 mole of copper that we're creating, we need 2 moles of electrons. Okay, let me erase this here so that I can keep going, because what we want is grams of copper. So moles of copper to grams of copper. In 1 mole there are 63.55 grams of copper. Okay, so that should take care of everything, and then all we have to do is solve for this. So you should end up with 3 sig figs in the beginning, so 3.56 grams of copper being produced. Alright, so again, we don't have to worry about the amps and the seconds there because they're giving us the charge to begin with, and we can go straight from the charge to moles of electrons because each electron has a specific charge. Okay, how many grams of Ca metal are produced by the electrolysis of molten CaBr2 using 0.187 faradays of electrical charge? Okay, that's interesting. So again, balanced chemical equation is what we're going to start with here. Alright, so we've got calcium. CaBr2, again, is going to have dissociated at this point because it's a molten solution of it. Okay, so we've got Ca2 plus and we've got Br minus. Technically, we've got two Br minuses here when this thing dissociates. And it's dissociating because we melted it. Molten means that we melted it. So there's no water in that solution. Okay. So we've got Ca2 plus, and we want to make solid calcium metal. So again, adding 2 electrons, this thing is getting reduced, so it's going to be solid calcium. So there's our chemical equation that we need for this one. Now what we've got here is 0.187 faradays of electrical charge. Okay, Faraday is basically synonymous with moles of electrons. Okay, because 1 Faraday is 96,500 coulombs. Okay, so when they say 0.187 faradays, basically what they're telling us is that's 0.187 moles of electrons. Okay, and it would be good for you to know that. So then, this is actually really easy at this point. So we go from moles of electrons to moles of the calcium. Okay, and again, it's for every 1 mole of calcium, there are 2 moles of electrons. And then we can go straight from moles of calcium to grams of calcium. And it's 40.1 approximately. 0.187 divided by 2 times 40.1. So 3.75 grams of calcium. Okay. I'm going to save the rest of these for 5th hour. Let's see how many we have left. 3. Okay, and those are pretty tough ones, so yeah, I think I'm going to save those for the last video. Hopefully what we did makes sense. I think all this middle stuff I think you guys will be fine with. It's the ones at the end are a little tricky.